Hello everybody and welcome to Statistically Speaking. Today we're going to talk about estimating variance and standard deviation. I talked in the last video about variance and standard deviation, what that is and all that. But in some cases we do not have the true values for the different distributions and all that we're working with. So in those cases we need to estimate it. So in this case we will think that we have taken a sample. We have taken a few values from the entire population and we will use those to estimate what the variance and standard deviation would probably be around. So here we have an example where we have 5 numbers. We have 13, 8, 19, 19 and 14. And we want to estimate what would the variance of this be. And the formula we would use S squared. That is usually how we denote the estimated variance. We can also write sigma square with a hat on it. It means the same thing. We usually use the hat to show that we're giving an estimate of something. But this formula that we would use in this case would be 1 divided by n minus 1 times the sum where we have I is equal 1 to n, where n is the number of numbers we have, xi minus x bar square. X bar is our estimated mean. So we can use this formula, just straight up, we calculate what is the mean, and then we calculate for each single one. Okay, we have 13 minus the mean squared plus 8 minus the mean squared plus 19 minus the mean and so on. We can, however, also write this formula in another way, and when we have few numbers it doesn't really matter which way we write it, but when we have many numbers this other way might actually be easier. So we have 1 divided by n minus 1 still, but this sum we change around a bit. So we're gonna have, actually we will have a parenthesis. So we have sum I is equal 1 to n of xi squared. So we just square our xi's. Just do that. Minus n times x bar square. And this is often more easy, because then we just take, okay, we have 13 squared plus 8 squared plus 19 squared and so on, and then minus n, the number of numbers, times the mean squared. So if we would calculate this example, with this case, I will use this formula. We need to know what is our n, and that is the number of numbers, that is 5. We need to know the sum of xi squared, or if we do that we only need the x bar, but we will use this in this case. And the sum of xi squared will be 13 squared plus 8 squared plus 19 squared plus 19 squared plus 14 squared. And we just calculate that with a calculator. And we would get 1151. And then we also need the x bar. And the x bar, we use the formula 1 divided by n sum I is equal 1 to n of xi. And I also have a video about how to calculate that, so you can check that if you're unsure about how the formula works. But if we calculate it, we would get 14.6. And then we have all the numbers we would need to calculate what would the variance in this case be. So if we would calculate this variance then, we would have, just gonna zoom out a little, we will get s squared is equal to 1 divided by 5 minus 1. The sum of xi squared was 1151 minus 5. Our x bar was 14.6, and then we square that. And then we just calculate this, and we would get 21.3. And that would be our variance in this case. But like I mentioned in the variance and deviation video, the variance is usually not that easy to interpret. What does that mean? The easiest is to do the standard deviation, and the standard deviation is just the square root of the variance. So if I would do that in this case, let's give us some space here. So we have s is equal to square root of s squared, which is equal to square root of 21.3, which is equal to 4.6152 if we round it up, something along that line. So we could say that this dataset varies around 4.6 between the numbers, which seems quite reasonable. We have a few quite small numbers and then a few quite large numbers, so this 4.6 seems to calculate how much this varies pretty well. So here we have another example. In this case, let's say we throw a dice. We have the different values we can get. We can get 1, 2, 3, 4, 5, 6. And then we just note down how many 1s did we get, how many 2s, and so on. And let's say now we want to estimate what the variance is. Well, what we could do the same as before. We just have 1, 1, 1, 1, 1, 10 times, 2, 2, 2, 2, 2, 18 times, and so on. So just like we had an easier formula when we calculate the mean, when we have this frequency table, we also have a similar case with the variance. Because you might remember that we calculated the x-bar when we had the frequency as 1 divided by n sum of fi xi, where we just take we have all our x's and then we times it by the number of frequencies, and then we sum all of those together and then divide by n, where n is the number of numbers. And in this case, n would be the sum of fi. So let's look at how the formula would look if we want to calculate the variance. We have our s squared is equal to 1 divided by n minus 1, and then we have sum I is equal 1 to k, and we have I equals 1 to k here, of course, also. I equals 1 to k, where k is just the number of classes, you could say. So we have 1, 2, 3, 4, 5, 6 classes. And then we have fi xi minus x bar squared. So you might see that it's very similar as with the difference between x bar with or without the fi. We just put in the fi, so we don't have to calculate this so many times, and same here. We just put it in the formula. But just like the last one, we can also simplify this. If we would have many different classes, then this can be a little tiring to calculate. So the other formula we could use that gives us the same thing would be 1 divided by n minus 1 sum from I equals 1 to k of fi xi squared minus n x bar squared. So we just put in the fi in the xi squared. So it's pretty much the same as before. We just add that fi to simplify things for us. So let's do this example to see what would this variance be. So first off, what is our n? Well, we know that it is the sum of fi. So it's 10 plus 18 plus 11 plus 17 plus 14 plus 20. And that is 90. And then we want our sum fi xi squared. And that would be, so we have 10 times 1 squared plus 18 times 2 squared plus, and so on. I'm not going to write down every single one. The last one, however, would be 20 times 6 squared. And this would be 1523. And we also need to know what is our x bar. So we use the formula that we had up there. So we have our 10 times 1 plus 18 times 2 and so on divided by 90. And that would give us 337 divided by 90. This gives us a very long decimal number, but since we're not finished with the calculations, I choose to have it in this form, just so we can get as good of an estimate in the end as possible. So, if we then calculate what is our x squared, we would get 1 divided by 90 minus 1, and the sum of fi xi squared, that was 1523, minus n is 90, and x bar is 337 divided by 90 squared. And that would then give us 2.934, around there. There are very many decimals, so I'm just gonna put down a few of them. But just like the last case, it's easier to interpret the standard deviation than the variance. So we're gonna take the square root of it. I'm gonna do that here. So s is the square root of our variance, so square root of 2.934, and that would give us about 1.7, around there. And if we look at this example, 1.7, it's almost about 2. I mean, that seems reasonable that it varies around there at average. It seems like a reasonable number. So that was some simple examples about how we estimate the variance and standard deviation. In many cases we have way more numbers than this, but this gives an understanding of how the formulas work and how we use them. So I hope that helped.